All right, today I have with us Dr. Craig Savage, who's a physicist here at the Australian National University. And one of the things he's developed is some visualization tools to look at relativity in sort of a real world way. And so, Craig, why don't you take us on the sea highway here?
Sure. Well, this is what I call the desert road simulation. And this is an artificial world, sort of like a computer game world, in which we've artificially made the speed of light 1 meter per second. So instead of being 300,000 kilometers per second, it's just 1 meter per second. So this is a very unusual world. But apart from that, everything is physically correct. And in this little movie, what we're going to do is accelerate down the road that you can see there. So we're going to start off some distance back from where you can see in the image at the moment. And we're just going to start from rest and keep accelerating down that road and look and see what happens.
Okay,
So I'll start it up.
As I see here, we have checkmarked aberration. So aberration is distortion
Right.
caused by the fact that things get lengthened or shortened.
That's right. Well, ultimately, it's caused by the fact that we're traveling at a speed near the speed at which the light is traveling. So normally in everyday life, the speed of light is so fast that it doesn't matter how fast we're traveling. Light is just traveling essentially infinitely fast. In this world, it's different. As soon as we start moving, our relative motion to the light actually starts to matter.
Okay, so let's see what happens.
So I'll start up, and what you've got to remember in this, because it's very unusual, is that we're starting from rest and constantly accelerating towards the front, towards the building. But you can see it looks like it's getting further away.
It's getting
But
further away.
we only ever are moving towards it. At the top right is our speed, is a fraction of the speed of light. C means the speed of light. And down at the bottom is the gamma factor, which I think you've encountered
we've
before.
discussed, yeah.
That tells you how strong the relativistic effects are. The hole in the clouds that you can see started off when we were at rest directly above us, and now it's in front of us. You can see these strange curving and aberration effects that are occurring.
We're right now passing the building, it
I'm
seems.
going to pause it so we can talk about that.
Yeah.
The little inset that's just next to you, Brian,
Down here.
there's a green arrow there which shows the direction of motion. That's us. And
Yep.
you can perhaps see the building. It's really a little map.
So this is the building here.
That's the building. So this is in the rest frame of the building, or the world frame.
Yep.
And the purple pyramid shows the field of view of the camera. So that's what we're seeing on the main screen. So what you can see right now at this point where I've paused it, and we're traveling at 0.946 the speed of light, although we're paused, so we're not actually moving, but everything, it's just like we've stopped the motion. You can see that the building's behind us in the world frame.
Right.
But we can see the building in front of us. So we're seeing behind us, and that's one of the magic things in relativity.
And
You can
that's
see
sort of
behind you.
what's really going on here is the light here was emitted, and we've sort of caught up to it at some level. It's
That's
ended up
right.
trying to go like that, and we're going like that, and we ended up meeting up here in the forward.
That's
and
right.
that's one of the things that causes that aberration.
And that'll become a little bit clearer
Yeah.
as we look at some more stuff. But it's quite mind-boggling that once you start moving around at the same speed as light is moving, you can even see behind you.
Okay.
So I'll keep that going now.
Yep.
I'll just
All right,
finish that
so
off.
we're going, keep going. Things are,
Now, this one is what it would really look like if all the physics was in there, except we've got the speed of light 1 meter per second. So it's still that artificial speed. But previously, I'd turned off the relativistic Doppler effect, which is a change in color. And I'd also turned off something called the headlight effect, or sometimes the beaming effect, which is an intensity change. And you'll see why I've turned them off once
so
I
that
show you the movie.
intensity, just to remind people, we know what the Doppler effect is. That's the stretching. But if I'm coming towards a light, as I'm going towards it very quickly, I get more and more photons per second
Correct.
coming from that light. So that's going to make the light much brighter.
It is,
Right.
yes, that's right.
Okay.
And you'll see that when I turn all those things on, it's kind of less interesting, or at least it's hard to see the aberration effects that we saw before. So this is the more realistic one, but it's a little bit harder to understand.
Okay.
So we'll let it go, but otherwise it's exactly the same. We're just going to accelerate down the road. Again, you can see things look like they're getting further away, even though they're not. You can now see colors starting to change, and the major effect is the brightening directly in front of us.
Right.
And as we accelerate more and more, it just gets brighter and brighter in front of us and dimmer behind us.
And it becomes more and more concentrated the closer to the speed of light we get. And we get this really bright thing where everything coming towards us is incredibly bright.
And you can see a slight Doppler rainbow around
Right.
that bright bit as well.
And
as
although we can see behind us, we really almost can't, because although light is coming from behind us, it's so faint
That's
that
right.
it's almost impossible
right.
to see.
That's right. So
Okay.
moving on, this animation, which all this stuff I must say was created by Anthony Searle, who I think you taught a long time ago.
He took this class back in the 1990s when I first started teaching it. Yes,
That's right. Anthony did some pretty amazing work creating the software which produced these videos. In fact, he was integral to everything we're going to see today.
And he did this as an undergraduate.
He did this as an undergraduate in the second year. In fact, it was over an Easter weekend where he dropped into my office on the Easter Thursday and asked what I was doing. And I said I was trying to create simulations of relativity, and didn't know how to do it. I couldn't do it. And he managed to do it over the Easter weekend. I don't think he slept much, but he came in on the Tuesday morning and had a working application which did everything I'd been trying to do for a long time, and I was just absolutely blown away. And the project has gone on from there. But Anthony wanted to use the tram motif, the idea that Einstein had thought about motion in terms of trams moving through Bern, the city in which he lived in Switzerland. And what you can see when you look at these images of the tram is how it changes. In fact, what you're seeing right now in that stop motion is a length contracted tram. So the tram is moving at about 86% the speed of light.
Yep.
So the length contraction factor is about 2, so it's half its normal size.
Okay. So let's put the image in motion and get a sense of how it goes. So
Yep.
we can see
And
there's all sorts of
it'll repeat through.
interesting effects. So as it goes by, it actually sort of it gets squished.
It's going to come in again. There we go.
Comes through.
And you can see that as it gets towards the center, we see the true length contraction. What we're seeing at this point in the frame is length contraction mixed up with some speed of light effects, so some relativistic optic effects, so it looks longer. But actually in the center, what you see is the pure length contraction effect. And you might also notice that we can see the back of the tram at this point.
We can see the back of the
You
tram,
can see the back of the
even
tram.
though it's sort of in a place where you normally wouldn't be able to see it.
Non-relativistically, you should be able to see the front of the tram from this perspective, but not the back. But relativistically, it's the other way around. And that's something called teral rotation. The objects appear not only to length contract, but also to rotate around.
Okay.
I'll
Put
continue
it
that.
through, and as it goes by,
Length
it gets
contraction.
that length contraction, gets squished, goes out of frame. So
Now we're jumping into the perspective of the tram and try and understand a bit more the things that we've been seeing so far. So this shows what you might think of as rain falling down vertically, but you could also think of it as photons of light
as
falling
light.
down vertically. These are the photons that get into your eye or into the camera, enable you to see things. And what we're going to do is jump into the frame of the tram, that is, move along with the tram and look at what happens to those
So here we're
raindrops
looking at
or
it from the
photons.
perspective of just standing outside and watching the tram go by.
Now we've jumped into the tram frame, and if you look carefully, you can see that those raindrops or their photons are falling down diagonally.
Right.
That's a very familiar effect. If you ride your bike through the rain or drive your car through the rain, you see exactly the same thing. The apparent angle of those raindrops changes. They seem to come
all the
from
rain
front.
always hits the front windscreen, not the back windscreen of the vehicle.
Photons are very much like rain.
Yeah, okay.
So they do the same thing. They rotate around so that from the perspective of you moving through the rain or through the light, you see it rotate around in front of you.
Okay.
Now this diagram here, I'll move it back a little bit so that we can start from rest. This shows light coming from a 360-degree circle around you. The green dot is us.
Yep.
And we're going to be accelerating through this animation, and what will happen is the direction we see the light coming from for each of those arrows will rotate around to where we see it coming from. In the world frame, it's always coming in like this, but as we accelerate, the aberration effect, or that raindrop effect that we just saw, happens, and this is what happens. Keep your eye on the arrow at the back.
All right. So we're going through, and we have light coming in all directions around us. And as we get closer and closer to the speed of light, it seems, because of the aberration, that things behind us are put in front, and that collapses all the light to be concentrated in that little headlight effect that we saw, the searchlight effect that we saw.
That's right.
And so that's why things look so bright here,
And
is all the light is
no
concentrated.
arrows back here, so it's very dark back here. So
Yep.
bright in front, as we saw, dark behind. And remember this arrow? It started off back here. we're now seeing in front of us something that in the rest frame or world frame is behind us. And that's exactly what we saw on the first Desert Road
We
animation.
managed to collapse the entirety of the sky, more or less, all the way into that
That's
little
correct.
bit
That's
in front
correct.
of us.
And it just keeps going as you get closer and closer to the speed of light.
And interestingly enough, is that in our first set of lectures, when we just talked about one of the ideas of gamma ray bursts, is that instead of, you know, traveling, if you're traveling very fast and instead of the light around, you put a light bulb here, and you figure out what it's going to do exactly the same thing as what it sees. And so that means all the light, that in the light bulb, almost none of it will go back here. All of it will be pushed out here.
Correct.
and
You just reverse the
beamed.
direction of everything.
That's right. So it
Yeah.
ends up looking like a searchlight, a little light bulb,
That's
to the
correct.
same effect. Okay, great.
Okay, so that's the end of these videos.
Okay, well, my understanding is we can go through and we can play around a little bit in real time.
We can.
And so I'm going to let you do that here
Great.
now. Thanks.
Excellent.